Hi, today I'm going to present the paper called Psi-Zero, Open Foundation Model for Universal Humanoid Loco-Manipulation. This is a recent work from people at NVIDIA and USC Lab that came out in March 2026. Now, regarding the research context, in this case, we're interested in humanoid loco-manipulation. So let me break it down. So we have the humanoid part, which is the target morphology of the robot that we're going to be using, that's being used in this research. And loco-manipulation, that is the combination of both locomotion, which is how to move your body in the environment, and manipulation, which is generally speaking about interacting with the objects. So it's not only tasks that interact with objects, it's not only tasks that move around, it's tasks that do both together to do the task. So in this case, this is a figure from the paper. We see that the robot has to move, get the object, and go back to a cart, put the object in the cart, or go up to the fridge, open up the fridge, pick up the object. So these are more complex tasks than some short horizon tasks that we also see in robotics. And this is interesting because humanoids, first of all, have the morphology that is closest to humans compared to other types of robots. That means that they're able, that they can fit in the environment that humans naturally live in, because we made the world for us. So it makes sense that if we can get a robot that has similarity in terms of its physical attributes with us, then it can more easily be deployed in our environments. Now, in order to solve this problem, there are multiple challenges that you face. The first one is the data scarcity. So a common approach when you want to train a model to learn how to do these long horizon tasks is you first need to collect some data by manually, so yourself, the human, have to manually collect data by doing the task yourself. And then you do this by wearing some type of suit or sensors. In this case, it's some approach from a prior work called Twist, where the human has to wear the suit, do the task multiple times, like many times, and then with the collected data, then we can train a model to imitate via imitation learning to do the task. And this works well, but it's hard to scale the number of data and tasks that the robots can do because what we call a robot teleoperation, which is this process of collecting the data manually, is expensive and hard to scale. Now, there's another challenge, which is the embodiment gap. That is, we have a lot of human videos available, either on YouTube or anywhere on the internet. But unfortunately, robots have fundamentally different kinematics and dynamics. So it's, even though in this case, humanoids have a closer morphology to humans, which helps, it's still not exactly the same. And although it doesn't look like an issue at first, there's actually many edge cases that comes with this distinction. For instance, the way we move our thumb or hand might not map one-to-one with how the robot would move it. And so this creates this embodiment gap. So we have to learn how to leverage this existing data while also making sure it works on the robot. Now, there was some prior work, which were not mentioned in the paper that I'm presenting, but I thought I'd include it. Some prior work attempted to solve this by first converting the trajectories collected by the human into a representation in simulation, and then they train a policy to learn from this data in simulation. So this was one way to tackle the challenge. Some other work, what they did is, instead of collecting the data using some suit, they just recorded themselves and then extracted the motions, the human motions from this video, and then converted these motions into a simulation-ready format to train a policy, which is a model. Now, some prior work limitations that are tackled in this work is that prior work, what they will do, for instance, we have Psi-Zero 0.5 and Groot 1.6 and 1.7. What they will do is they will use what's called co-training, which is basically you train a model using a mix of data, because we have a lot of human data available, like videos, and we have only a small portion of robot data available. So in order to have more data during training, we train with both data simultaneously. And for instance, we can predict the next action in the human data and the next action in the robot data. So we have one model that needs to pretty much learn two fundamentally different action distribution, and the paper identifies this as one key limitation of prior work, is that if you only have a monolithic model, you're for sure going to make some compromise when you're learning both at the same time. Now, the core contributions of this paper are as follow. We have that the main contribution, I would say, is the novel multi-stage training. So instead of doing co-training where you use all the data at the same time, they have a more, I would say, systematic approach of going of how you exactly use the data at each stages. They have multiple stages. Instead of one big stage, they have multiple stages where each stage will learn from different data. First stage will learn from human data. Second stage from robot data. They also have a better teleoperation setup. So as we saw, yes, you can use a suit, but when you use a suit, it's hard to also have what's called dexterous manipulation support. So it's hard to map exactly how your hands move precisely. So some suits don't even support that. And their method actually uses some gloves to have better dexterous manipulation. They also tackle the issue of real-time action execution. So what happens usually is they will train a big model to do these robot actions, to predict these robot actions, but these models are really big, and so they're very slow. Imagine using ChatGPT for moving every fiber in your hand, like every muscle fiber. It would take forever because every prompt, every response would take multiple seconds. And so this is addressed in this paper, and they also deploy it in the real world and show much better performance. Now their system, the way the method works is they have like three different system or three different level. The system 2 is they use a pre-trained VLM to learn good visual and textual representation, and generally speaking, just the semantic of the world. And then they have a system 1, which is what they call an action expert, which is a neural network that's purely focused on the robot data and learning those robot dynamics. And they also leverage prior work that basically already trains an RL policy to control the lower body of the robot, so like moving your legs. So this part here is the one they train. This one is always frozen, and this one is also being trained. And the data recipe goes as follow. First, we have about 800 hours of egocentric, so first-person view, human video data from EgoDex dataset. They use this to pre-train the VLM. It's actually they use Quen checkpoint, and then they train it on this egocentric human data. And then they do what's called post-training using the action expert on a humanoid everyday dataset. This dataset has multiple tasks, and the goal is to learn robot dynamics. And this dataset is much smaller. And then at the end, they fine-tune on in-domain teleoperated data using about 80 trajectories per task. And so the first stage in the multi-stage training is to train the VLM. So they start from Quen 3, 2 billion instruct checkpoint, and then they use the EgoDex data set so you have an image, or in this case, multiple frames from a video, task description, and the model predicts these discrete action tokens. So it's not continuous; it's a discretized set of actions, and so this gives sort of a human egocentric and human manipulation prior to the model, which it doesn't have initially. And once you trained your VLM, then you freeze it, so you no longer update the parameters, but you use the learned representations as input to the action expert. And this action expert has about 500 million parameters, so it's much smaller than the pre-trained VLM. And now you're predicting and learning to predict continuous action chunks. So now it's actually learning precise manipulation. It's not just discrete actions, which are like more broad. It's precisely controlling the robot. And this stage is then followed by a deployment where during deployment, they will use what I mentioned earlier, their System-Zero, which is an RL policy that's kind of already pre-trained to control the lower part of the robot. So this action expert will predict 28 degrees of freedom for the upper body joints. So it's going to predict the angle for each joints of the upper body. And it's also going to predict what we call commands for the low level, which could be like follow this velocity or something similar. So it's going to predict 8 different commands. And this pre-trained model is already an expert, quote, an expert at following these commands. And then it's going to predict the joint angles for the lower body. So together, the action expert predicts 28 degrees of freedom. The lower body policy predicts 15 degrees of freedom. So together, this gives 43 degrees of freedom action space, which is pretty big. Now for their teleop setup, what they use is what we see here. This is a figure from the paper. So they have a VR headset to get RGB, and they use Manus gloves, which are dexterous gloves, and they use waist tracker to have even further precision in their data, and to have foot tracker. And these are used to send to actually record the commands that are then going to be sent into this System-Zero policy only for training. So this is only to collect the training data during inference. When we deploy it to the robot, then we don't have this setup here. This is only to collect the data. Now regarding the real-time chunking contribution, basically the gist of this is that, like I said, big models are slow, and so what would happen is the big model would predict like a chunk of actions, so like a sequence of actions in one go, and the robot would start executing the chunk, so the big sequence of action. But then at some point during the execution of this chunk, we're not going to wait for this whole chunk to be done and then re-query the big model, because then what would happen if we would do that is we would execute the chunk and then ask the model again, okay, what actions do I need to do? And so there would be this execute, stop, think, execute, stop, think, which would be very jittery. And so what's commonly done is while we're executing the action, we already start predicting new actions. But what we see is that when this is being done, so even using this trick, what we see is that the first few actions will sort of make sense together, but then a new chunk will be predicted, and this new chunk is being predicted independently of the first chunk that was being executed. So we might see like the arm starting somewhere and then stopping and abruptly changing direction. And this is what we see in this graph here. So we see on the y-axis is the joint angles. So we see that initially it's following a trajectory, and then, this new chunk was just predicted. So we start executing this new chunk, and now we're completely changing the angle in a very unnatural, not smooth manner. And so to address this, what they did is when they predict a chunk, they execute, some actions, and then they start predicting the new chunk while they're executing the actions. But the new chunk is being predicted conditioned on the already executed actions. So the model learns that, okay, I'm predicting this new chunk of actions given that these actions were already executed, such that the new chunk is can smoothly blend with the already predicted actions. And in red is their method. We see that the new chunk kind of follows the orange, which was the previous chunk. So we see that it follows more closely what was previously predicted, such that it's much more smooth. Now, regarding the evaluation, they only evaluated it in the real world, not in simulation, and they came up with 8 different long horizon tasks that, when we say long horizon, it goes beyond 2,000 steps, basically, at 30 hertz. And so we see that these are fairly long tasks, and to do one of these tasks, there are multiple subtasks that you need to master, that you need to do correctly in order for the entire task to be success. Now, regarding the results, in this red-ish color is their method. In green is Groot 1.6, which is another, it was pretty much state-of-the-art method for humanoids. Pi 0.5 is also a very strong method. Although all of these methods were fine-tuned, that is, with the same data, but they were pre-trained with their own data sets. Only the fine-tuned data is the same. And Pi 0.5 was pre-trained with not humanoid data, with like tabletop manipulation and dual arm tabletop manipulation. But the Pi 0.5 paper also says that it can be used with humanoid if you have humanoid data. So it's still fair to compare it to Pi 0.5. In fact, it's a good baseline to have. But Groot 1.6, I would say, is a more humanoid native method. So it's impressive to see that it's doing much better than Groot 1.6 across the board. In some tasks, Groot is actually completely failing, whereas this method is almost reaching like 90%. So overall, the paper says that they improved by about 40%. And this is success rate. I forgot to mention the y-axis is success rate over all of the tasks. And they perform 10 rollouts per task and then average it to get a single numerical value. And they say they get 40% increase in success rate on average compared to Group 1.6 while using 10x less data. So this is important because this goes back to the earlier mention of using all of the data together, human data plus robot when training, versus doing this more systematic approach of pre-training the VLM with the human data and then learning this action expert with robot only data. So we see that the gains here are not obtained from scale, basically. So this is a bit contradictory to some of the recent, I would say, success that we see in robotics and even LLMs, where you would assume that, okay, just scale the data, scale the model, and we get better performance. But in this case, they show that scaling blindly is not the right way to go about this. Now, they also show some real-world results, which were pretty convincing. Overall, the robot is able to maintain fairly stable pose, and we don't see any jitter or any unstable motions. So this is always good to see. Real-world evaluation is very hard, especially because you have to make sure, like, all of the data that you collect during training might not even be calibrated the same way that your robot is going to be calibrated. So there's a lot that can go wrong, but their method seems to be doing quite well in the real world. So I would say this is very impressive results, because a lot of papers also only evaluate in simulation. So it's good to have real world evaluation here. Although one thing I will point out, and this was not acknowledged in the paper, is that a lot of these tasks have very, I would say, easy locomotion. So it's, I would say, a fairly manipulation heavy benchmark. And their method, if you remember this part here, the lower body, so responsible for locomotion, was just a pre-trained model that they did not train. So their method is most interested about, yes, loco-manipulation, but I would say manipulation heavy. And so it's possible that their benchmark is kind of biased towards what their method would be slightly better. Now, regarding the strength of their method, it's very efficient. I mean, they get 40% better success rate with 10x less data. That's undeniable. They also fixed the jittery motions that we all pretty much always see when deploying VLAs, which is vision language action models, to the real world. And they say they're going to open source their code and hardware. So, I mean, the hardware part is the G1, but the software is going to be open source. So that's good because the community is going to be able to build on top of this. Some limitations in future work. They don't perform multiple tasks in zero shot, meaning they always have to fine tune using some task specific data that they obtain using teleoperation. So they're not completely solving that issue. Also, they acknowledge that the G1, which is the robot, has limited, weight capacity. It's about 3 kg per arm, a little bit more if you're doing like whole body coordination, but it's still a limitation. Also, a limitation that was not acknowledged in the paper is that They don't train a single model that controls both the upper body and the lower body. Like we saw, they use a pre-trained model for lower body and only train for upper body for precise and manipulation and also to output commands for the lower body. So the main takeaway is that effective scaling requires scaling the right data in the right way. So you cannot just blindly scale. Real-time control can be achieved even with big VLA models with an asterisk because the lower body is being controlled not by the VLA. And yeah, freezing the VLM and just fine-tuning it results in poor performance. So the order and the staging of the training matters. So in conclusion, this paper is promising work and it introduced some clever techniques that were much more data efficient, and it shared good insights. So I think this will help overall the research community. And that concludes the presentation. Thank you.